This is both example 10.7 and problem 21 in chapter 10, which a father is spinning a merry-go-round and we're trying to find out what's going on. He's using a force of 250 newtons to pull tangentially on the merry-go-round, which has a radius of 1.5 meters. So that'll create a torque, and that torque will then accelerate rotationally accelerate the merry-go-round. We're supposed to calculate the angular acceleration in two situations, one when it's just the merry-go-round and then one when the child, an 18 kilogram child, is on as well. So there's a little beginning work here. First we have to calculate the torque, and the torque is this force acting at this distance. So torque is just the product of those. That equals F times R, which equals, in this case, F is perpendicular. So that's 250 newtons times 1.5, which equals 375. And that's newtons meters. Okay, so that's the torque, which is going to cause the merry-go-round to accelerate. Now we also need to know the moment of inertia of the merry-go-round, which is 1/2 mr squared. We're treating that as a disk. The moment of inertia of a disk is 1/2 mr squared. When I use m equals 50 kilograms and r equals 1.5, that turns into 56.25, and the units are kilograms meters squared. Now, tau equals I alpha. This is just Newton's law applied to the rotation. Tau is the equivalent of force. I, the moment of inertia, is equivalent to mass, the measure of inertia. And angular acceleration alpha is this equivalent to linear acceleration. So in this situation, alpha equals tau over I, which is 375 newton meters divided by 56.25 kilograms, and we get 6.67 radians per second squared. We also want to know what happens when we change this problem and we put a child on the merry-go-round. So in this case, we're going to add the I of the child. This is considered as a point mass, just a mass that's acting at a point, and so its moment of inertia is mr squared, the mass of the child times the radius of where they are relative to the axis of the merry-go-round. In this case, it's an 18 kilogram child at 1.2 meters squared, and so we end up getting a moment of inertia of 28.12, and that's kilogram meter squared again. So the total moment of inertia is the I of the disk plus the I of the child, which when you add those up, that adds up to 84.4 kilogram meters squared. Now when I find alpha of the merry-go-round and the child together, that's the same torque over the new moment of inertia. So 375 newton meters divided by 84.4 kilogram meters per second, which is 4.4 radians per second squared. So that was example 10.7. Now we go on to problem 21, and they ask, what's the kinetic energy of the child on the merry-go-round, the child and the merry-go-round, if they have a revolution of angular velocity of 20 RPM. We'd need to convert that to radians per second, so we'd multiply that by 2 pi radians, 6.28, and we divide that by 60 seconds, and we'd end up with 2.1 radians per second. the kinetic energy of something that's turning is just 1/2 I omega squared. I is the I total here. When you plug those numbers in, you get 185 joules. We also want to know that if I applied a force against the side of the merry-go-round, how's it going to stop? So in this situation, we want to see that we're going to look at it from a different point of view. The father will apply the same force, but in the opposite direction. So in this case, the force is this way, 250 newtons. It's acting at a radius, so it creates the same torque, just in the negative direction. So if the merry-go-round is spinning this way, then it's going to slow down and reduce its speed. So the question is, can we use energy to look at this and determine how long it takes, or how much the forces it requires to stop it? Sorry, how many rotations it'll take to stop it. Now, work is force times distance. So if we look at angular work, W, instead of force we have torque, and instead of distance we have the angle theta through which the distance is applied. So if I want to solve for theta, theta just equals the work over the torque. Now we know the work. If I have a total energy in this system of 185 joules, and I want it to come to rest so that the kinetic energy is 0, that happens because the father puts this force on, creates work in the opposite direction. So the work equals 185 joules. Then I also know the torque, which is 375 Newton meters. So that becomes 0.49 radians. And if I wanted to convert it to revolutions, it's divided by 6.28. That's 2 pi, or 0.78078 revolutions. So can stop it fairly quickly.